Hello, everyone. I'm Abhishek, and I, along with my colleagues Gunjan Chablani and Harshit Pandey, will be taking you on a tour of our toolkit for diachronic analysis of scientific literature. This paper was a joint effort of my friends Gunjan, Harshit, Rajaswa, and me from two universities of India, BITS Pilani and University of Pune. You can visit the repository by scanning the QR code on the bottom right. Before we dive deeper into the applications of the toolkit, let me walk you through what inspired us to make it. The app is called DRIFT, an acronym derived from Diachronic Analysis of Scientific Literature. Now, research trends change and shift over time. New concepts emerge, old concepts are forgotten, sometimes to be magically revived again. An example of this is neural networks, which were first introduced by Rosenblatt way back in 1958. Neural networks spent their time in the wilderness before they were revived in 1986 with the invention of backprop. Changes in research trends could be due to various reasons. It could be because of a lack of resources or a novel concept not gaining traction in a particular period and its worth only being recognized decades later. And that is the focus of our paper, studying emerging and declining trends. There has been significant research done in analyzing research trends. Off the cuff, a few papers and resources which come to mind are NLP for NLP and NLP Scholar, both of which perform a citation-based analysis or answer questions such as diversity in the researching world. Other papers also employ statistical methods such as using frequency and productivity techniques to gain insights on emerging or declining trends. However, there isn't a very user-friendly app which combines statistical techniques and temporal word embeddings-based techniques to study research papers and extract vital components from them and monitor trends and patterns of development in scientific literature. Drift does that for you. The salient features of Drift include ease of usage and flexibility. The app is very intuitive to use, and users can run the analysis methods by just clicking a few buttons. The app is also very flexible because users can upload their own corpus on which they want to perform the analysis and train the TWEC model. For every analysis method, we provide multiple options and customizations, such as different dimensionality reduction techniques, for example, PCATS and EUMAP, for plotting word embeddings. Drift has two modes, training mode and analysis mode. The user can upload his or her corpus year-wise, run a pre-processing pipeline before training the TWEC model. Once a user has trained the model, he or she can switch over to the analysis mode and run one of the 9 methods which our app currently has. We plan on adding more analysis methods soon. For training temporal word embeddings, we use TWEC or temporal word embeddings with a compass. In most temporal embedding training methods, the main issue is that word embeddings of different years belong to different coordinate systems, and aligning these embeddings is a huge challenge. TWEC does it in a very simple way. For our work, we train it on data for all the years to learn atemporal embeddings. Then the trained target embeddings are frozen, which serves as a compass, and temporal embeddings are learned for each year as context embeddings. The dataset we used was crawled off of arXiv. We crawl papers belonging to the CS.cl or the computational linguistics domain. To perform our analysis, we only consider the abstracts because abstracts convey the gist or the crux of the paper, and the rest of the paper may contain tables, figures, equations, which are difficult to handle. We consider only 27,000 papers between the years 1994 and 2021. Now, my colleague Harshit will show you a demo of some of the analysis methods in Drift.
Firstly, let's talk about the productivity plot. The purpose of this method is to classify terms into 3 categories that will describe if a term is growing, consolidated, or declining with respect to its time period. To do this, let's understand 2 important terms that are required to classify each point. The frequency is the number of times a term, unigram, bigram, or trigram has appeared in the corpus for that selected time period. Productivity is the other important term, which is a measure of the concept of an ability to produce new terms. It can be explained with this formula, this entropy, and this formula is explained further in the reference paper given for more details and intuitions. And based on these 2 measures, we hypothesize 3 kinds of terms: growing terms, consolidated terms, and terms in decline. Growing terms have increasing frequency and productivity. consolidated terms increase in frequency but not productivity, and declining terms have an upper bound for productivity, but they've started to reduce in frequency. So now we'll be giving an example of productivity. For example, here we can see BERT is an increasing, is a growing term because its productivity and frequency is increasing because of the rise in popularity of transformers over the last few years. Next, we can see LSTMs. LSTMs have basically stagnated in the productivity and it's started to go down. It was once popular, but it's been replaced by transformer models now. And now, the term train has basically stagnated in popularity, but the frequency keeps increasing because, of course, the number of machine learning papers every year are increasing. So we can say that train is a consolidated term. Using diachronic embeddings of a term, we can find out how much a term has gotten closer or further from another term. Acceleration of a term is used to identify fast conversion keywords. If acceleration is greater than 0, then we can say that the terms are moving closer to each other. Acceleration is simply the difference between the cosine similarities of the initial year and the final year over here. In this example that we see here, translation has shifted closer towards attention between the years of 2015 and 2021. This method helps us define the change in meanings of words over the years. This could be due to changes in social or cultural factors, with new words being introduced or old words changing their meaning as a result of research or pop culture. So this is the way that the algorithm works. We have all the words and the initial year and the final year. We take the word embeddings from the first year, and we take the word embeddings from the final year of the same given words, and we find the Euclidean distance between them, and we store it into the dictionary. This dictionary is basically sorted by value, and we return the top k most shifted words, the words that have had the most semantic difference. For example, in this the word model, model 1994 was close to Markov models and Bayesian models. So this was the state of model of 1994, and in model of 2021, we can see that it's closer to neural network architectures, transformer models like MBERT, XLNet, encoders, etc. I'll now explain the usage of the application. On the left side, we can select the analysis type. For in this example, we've selected semantic drift, and the About section will tell us more details about the formulas and the intuition behind the model. And in the plot parameters, we can select the range of years, the dimensionality method, along with the plot's title, etc. And now we can select what we want to analyze. So we've analyzed our own custom word, which is transformer, and we can see that the shift in the semantic shift in between the words.
The way in which terms tend to associate with each other may change over time due to change in semantic meaning. Plotting k-means clusters for a range of years helps us understand how the words are connected and how these connections change. Our tracking clusters method allows users to select words and plot clusters around them, as shown in the figure. In the example, we can see that between 2019 and 2020, the number of clusters have reduced, and terms like dataset and classification have moved to the cluster containing model and neural, and the word language has moved to the cluster containing semantic and knowledge. Another method that we have is tracked trends with similarity, which can be used to see a trajectory of words across years. The algorithm describes the process as a pseudocode. Basically, we iteratively select top k similar words and repeatedly ask the user to choose from those words within a given stretch to plot a trajectory. In the example below, we can see that the term model in 2010 was related to GMMs in 2011, and it eventually leads to ASR in 2017 and acoustic in 2019. This makes sense because earlier GMMs and HMM were used for automatic speech recognition, or ASR. This was a brief overview of the methods that we have included in the Drift toolkit. There are other methods that have been implemented, and we are currently planning to add even more methods so that researchers can benefit from them. Our future work will also include semi-automated inference from the results and easy integration with research papers and LaTeX. This brings us to the end of our presentation. Thank you.